a different parameter, a phase parameter here will occur is different for a different circle. Mostly they are 0. This gamma is 0. But in some case, especially the topological system, the gamma can be different. And this we call it Berry phase. So then if you follow this definition, the Berry phase can be defined as kind of Berry connection of 0 to t. But if you do this algebraically, you know that's partial r, and this we call Berry connection. And you have dr. And this partial r dr is very good thing because you use a partial integral. So you can change the parameter here to k, or to difference to theta or something. So you know that first of all, the Berry phase is independent of the path of this circle. So if your circle is differently, but if you don't change the singularity inside, so then the Berry phase won't be changed. That's the first. A second, it didn't depend on the parameter you use. You can use like t, because you have partial t is the original definition partial t. But because of these terms, you know that you can change that to partial r or partial k. So then this is Z phase, and Z phase is eventually the Berry phase in the Brillouin zone, for the Brillouin zone. And then you can use like different phase. You even can use the Berry phase definition of you only change the two coupled of kind of you guess the phase of theta, and then you change that. So it doesn't depend on the parameter form. It doesn't depend on phase. It's a very pure topological property. So therefore, it's very good for us to understand the topological system. And for the P-wave superconductivity, 1D P-wave superconductivity, you can change the chemical potential, and you can change the pairing, and then you change the hopping, but you can choose one of them as the identity. So you divide by t, and we only change the chemical potential and then the pairing and define t equal to 1. So then you can have this phase diagram, and you can have phase 1, phase 2, phase 3, and phase 4. Difference of this is in the phase 1 you have Berry phase encircle the origin, and if it's encircle the origin, the Berry phase will be pi or minus pi. So then you know that if you change the different, but they won't change too much. It's only since that you encircle the origin. The origin is the singularity of this system. So then, but for the phase 3, phase 1 and phase 2 are different because of clarity of this. And this is the R1 and R2. I mean, R1 is eventually the parameter R dot sigma, and then if you have P-wave superconductivity, you have R3 equal to 0, then you have only 2 dimensions. And then this is so-called chiral symmetry of that. So then you have either encircle the origin or in the counterclockwise way or in the clockwise. And there's a difference of this 1 and 2. But both of them are topological, but they will go over a phase boundary of that. So then these two are 2 different phases. But for phase 3 and phase 4, you know that you won't encircle the origin, and then you get Berry phase only equal to 0. So then these 2 are not topological, and these 2 are topological but different. So we want to study the 1D P-wave superconductivity, and then this is still under debate. And then we have this classification of this topological phase, and according to the time reversal symmetry is broken, or chiral symmetry is broken, or particle symmetry is broken or not. And here's the particle symmetry is the chiral symmetry. So so then the old saying is that the P-wave broke the time reversal symmetry, so you have this, and then conserve time particle symmetry, and then you have this D class. But however, it changed because because if you have D wave, you won't actually broke time universal symmetry in the in the real time universal symmetry. So then now they change to this class, the BDI class. So it conserves particle symmetry and time universal symmetry and Chaos symmetry of these three. So that you get in the 1D you get Z. But I think it's still under debate. 1 year ago I still used the Z2, but now it's kind of they changed the classification of that. So in the topological system, you have different way to classify the topological system, if it's topological or not. One way is use Berry phase, but another way is you can use the H modes. So you just cut the system, into a block. In the one chain, you cut them of a very long chain, but you cut them with an open boundary, and then you see if it has a H mode, zero energy mode or not, if the chain is long enough. If you have the H mode, then you have topological system. This is one definition. But another definition is that for the periodic thermodynamic limit chain, so you just measure Berry phase. If you get some pi Berry phase, then you can have topological system. Eventually, these two can be proven. They have less like bulk H correspondence. Like you measure the bulk of the Berry phase, then if you cut them as an open boundary, then you get the H mode. So therefore, you have Berry phase pi, then you have zero energy state, and then you have for the 1D P wave, you have Marat fermion because you have this real fermion on the boundary, or you can call. But for Berry phase 0, then you have no zero energy state for the for the H, so then you won't have a Marat fermion. So then you see that the real Hazuka in 2002 mentioned this property, and this is very useful for us because we can use that to measure, kind of H mode in an information sense, and then we have this bulk H correspondence for the entanglement entropy spectra. So this is very important in our talk. So we want to talk about entanglement entropy spectra. So you have known what is the entanglement, you know what is topological system, but still a new concept will be formed is entanglement entropy spectra. So we know that entanglement formation is eventually for two systems, and you integrate out the B, and then you have reduced the entropy, and we measure the von Neumann entropy, and then we call it entanglement entropy. And I told you why it's related to the entanglement formation, how it is related to entanglement measurement. So for the quadratic model that we want to measure that, I think it's simplest one. But quadratic model has a very fun property and very interesting property because it's still many body effect inside. It's not really, though it's one body, but it's not really the one body of one bodies. You can call it some many body effect inside, and then you can indicate some property with the interaction. So we want to study that for quadratic model because it's also doable experimentally. Then the reduced entanglement can be separated to different modes, and these different modes you can do that because it's quadratic. You know that for a quadratic model, you integrate out, you use Gaussian integral, and then you have still a quadratic for A. So then the entanglement entropy is eventually you sum over different entanglement entropy, different entanglement of different modes. So then you add it together. So lambda m we call single particle entanglement spectra. It's different than many body because many body is you have to consider all of them. But if you only consider single mode, you have single particle entanglement spectra. It's very confusing, but if you think about Hamiltonian, and then you use like single particle Hamiltonian, you have single particle energy. Then the real many particle energy is that you have to derive product of those. You have add them together for the energy. So this is also similar. Like you have single particle entanglement spectra because you separate different modes, and the many particle spectra is that you consider the whole together. You have to use your pen and then to understand that. However, for the many particle entanglement, you have two of n dimension, but for many you have only n dimension for the system with n size. So how to do that? You can use the coherent state to integrate our degree of freedom environment B. Okay. We did that 2001 with my advice, PhD advisor, how to do this. And then using that, entanglement entropy actually can be obtained by diagonalize the Bloch-Green function matrix. I will introduce you what is Bloch-Green function matrix later in the next slide. So, but to do Henry and Chung in 2003 did that, the incorporation in 2003 did that, and then we extend that to different systems with pairing terms in 2006. So it's a whole process, but now it's fixed that you can really use this. Is already as a standard method for the recent years. Like if you want to understand TI of the quantum information property of TI, you really use that to understand that. So even Qi Xiaoliang, Fu Liang, they also use this method to measure the entanglement of the topological isolated. So, example of the Bloch-Green function matrix is that you have one chain, a very easy chain, and you have Hopkinton, and this black dot is the particle, and this circle is the empty side. So the particle can hop to different sides, and you want to know the entanglement of these two because of if you have this a fermion, you have Pauli inclusion principle, so still can measure some entanglement of that. So then you have this Hamiltonian. You can obtain the ground state of the whole Hamiltonian, and then you form a Bloch-Green function matrix. Eventually, you just want to calculate the correlation of Ci dagger Cj inside the system, and then you can get a green function, correlation function, and then because only inside the system, then you can diagonalize that, and you get eigenvalue lambda m, and this lambda m is eventually the one particle's entanglement spectra here, as I wrote in the next slide. So interesting thing is that if you extend B to empty and A extend to whole system, then you get that G is eventually the particle number, the eigenvalue of G is particle number. So it can be filled or not filled. So the box state is that you get G lambda as 0 or 1. But because you have this system finite, it's not for whole chain, so you get some eigenvalue between 1 and 0. So then this 1 and 0, or the other is 0 or 1, is the Bach property. But you get some of this 1 of 0, it indicates some communication between this environment and this system. And then you just add them together, then you, using the formula entropy, then you get the entanglement between these two. So then you get this form. And this form is very interesting because you can use that to prove GGE, general distance ensemble is right. So I really like this form because it helped me to solve this problem easily. So when I saw the GGE, I know this is for sure related to reduced density ratio. But this is another topic. So entanglement Hamiltonian is eventually the exponential of minus HA entanglement. So So then the eigenvalue for this one, we have solved that is the different mode of fermions. So this is a one particle entanglement spectra, and as I told you, it's this form related to the lambda m eigenvalue of this Bach-Green function in this form. So so if you want to find full entanglement spectra, you have to add different modes together. So it's kind of complicated, but the idea is so easy because you just have this one particle spectra and add them together as a many-body spectra. So entanglement spectra is like this. But this is only for the quadratic model. So you can imagine that you have Hamiltonian with interaction. So it won't be so simple because it cannot be separated to different like a quadratic model. But then you have to add the other terms here. But still, you can use the numerics to find the entanglement spectra. And this entanglement spectra is very interesting because it really can tell you the form Schmidt decomposition. A Schmidt decomposition is eventually you have the two, and then you find the state can be separated to the left-hand side and right-hand side, or different, and then you get this eta e here, and this is really related to the entanglement spectra we have mentioned above. So, and using this entanglement spectra for example, this Maurice state, and then just it's done by Lee and Houdet, and they found that the low energy spectra is really the same as the conformal theory of the Maurice state in the real system. So this is kind of copy of that, and then if you have the topological system, and then your entanglement spectra have this one in the low energy citation have this copy of the exact Hamiltonian, the Moritz Hamiltonian of the fractional quantum Hall effect. So then it can be used to identify if the system is topological or not. Use this. But however, this is only one example. You have example that cannot be like this, but for the gap state, because for the topological system, most systems are gaps. So for the gap state, we know if the gap is big enough, then this, the mimic of this original Hamiltonian in the entanglement spectra can be found really. So now we know that Bach-Green function matrix is very important for calculate the entanglement spectra. And then you find that if you, in the quadratic model, if you have Green function, and this Green function is eventually give you, in the Fourier space, give you very similar form of R dot sigma. Remember that you have R dot sigma in the Hamiltonian, and remember that you have Bach H correspondence. So then you have this very similar form, and this R dot sigma is the same as Hamiltonian. So you know there's some similar physics inside. The physics that R dot sigma is equal to 0, then you have 0 in its mode. If not, then you don't have. So, and this you divide by R is positive. So you know that the topology of this Hamiltonian, this Green function, the Green function can be effective Hamiltonian of that, and the topology of that is similar to the Hamiltonian with open boundary, but that only correspondence is the physics is not the same. As I said, the Green function is the measurement of one whole chain, and then you measure the entanglement of the system and environment. You just cut them, and this cut is the virtual cut. It's the major cut. So you cut them. So you have to diagonalize this Green function. But for the Hamiltonian, you have one chain, and you really made it open. Then you have open chain. So then you have this H state. So here, I mean, you have this alpha sigma. So then you have similar physics, but then you have correspondence. I mean, Berry phase is same. So G and H share the same eigenfunction. And if E equal to 0 for H, then lambda m equal to 1/2. So you have 0 any state for 0, then you have maximum entangled state because if lambda m is 1/2, you got maximum entangled Bell state for this mode. So then you have Majorana fermion for kinetic models for the open chain, then you have also Majorana fermion here for the measurement. So that means if you measure the system and then you cut them your system and environment, then in the measurement you create Majorana fermion, and this Majorana fermion really communicate the system and the environment as the most efficient quasi-particle. So then because this talk is kind of combination of different concepts, we want to talk about quantum quench, and you prepare a state and you quench the parameter of the Hamiltonian, and you let evolve with time that you get this. So now the eigenstate of H, so these two can not commute. So the important question that because now out of equilibrium physics is very difficult, but if you can really find a steady state to describe the out of equilibrium, then you are successful because normally we don't. And for the integral model, it's interesting because for integral models, you know that kind of state that can be formed. Then you calculate the expectation value of the time and divide by t. And then you want to know if there are some steady state to describe. If yes, if the steady state more like behave like kind of temperature here, then you can call this system thermalized. But the thermalized system have different definition. Well, this is the easiest way.
So this is an isolated system or your dissipative system?
Isolated system. You isolate because we don't study the open system. So this is isolated system. Okay. So interesting thing is that ergodic theory really, if you have ergodic, like your system go over all the phase space, and then mostly a state state will have this effective temperature and defined by the final Hamiltonian here. But for the integral model, you don't have ergodic system like a pendulum. You know that the pendulum they have only kind of circle in the phase space, so they don't have ergodic system. They don't go over all the phase point. So then normally you cannot get that. It's also the things we want to study. And then there's one example that you have this model. Actually, this is Tom Biardo case. You can really make that in the co-atom. So it's like you have bosons here, and then you have this optical lattice. And then because you can create the interaction of these two particles very strong, so therefore the two of them don't like to if 6 is on the same side, then you will expect that. So you have kind of hardcore bosons, and then you just stack this boson in a box, and in the time 0 you just extend this box, and that the system per side the same. So you can provide some other particle inside, and then you see that how it changed. Then we have a cartoon picture of that. So you do the Euler-Wigner transformation, and then this is the distribution of n of the x. X is the coordinate, and this is a distribution of a momentum space. You found through the time the distribution will really go to kind of steady state, and here the form is also steady state. And this form is not Gaussian, so it's not thermalized. And this we call is kind of we have a steady state to describe the system. And for the integral model, the steady state can be found as kind of GGE. And GGE is eventually proposed like constant motion, because for the integral model, constant motion It's very important if you know the classical mechanics. So constant motion, and then you find the parameter here can be designed by the initial condition here. So you know that for the thermalized state, you only depend on the temperature and the final Hamiltonian. But here, the GGE is the steady state. You see, the GGE will give you the best curve here. So then the GGE is the best description of the steady state, and this GGE depends on the initial condition. So they have memory effect, like the system of the integral system the integral system will remember the initial condition. So, okay, then this can be found. It can be described by GGE, general Gibbs ensemble. But this is only for the initial condition. How about age? That's what we want to study. So the age state. So how to calculate the memory of a Berry phase? So we know that you have to calculate the correlation function matrix Gij through the time. This is time dependent, and then you have to find that in the momentum space, and then you can write this R. You can calculate that. Not very easy, but it's kind of calculation inside. So then you find this is cosine and this sine is cosine. And then through the time, this time will dephase because most of the case, only kind of very special case, this side won't dephase. But if you do the average of time, then this also will disappear. And then you see only one term won't disappear. And this term will depend on the R and R prime and R prime. And this R is the initial R, and R prime is the final R prime, or final Hamiltonian. So that means the system can be co-decided by the initial state, initial Hamiltonian, and final Hamiltonian. Then they carry the memory effect of that. We call this effective R vector. And then the really things that this effective R vector really design the Berry phase and design the H mode. And then we can see in the picture here. So if you quench the system through the boundaries, we found that the effective parameter will always go over the origin, then it will give you 0 Berry phase, and then it won't have any H mode at the final time. You see the H mode is you don't have 1/2 H mode here. So this picture is very clear. So no thermalization appear. But very interesting thing is that you go inside the same phase. You have two different situations. One situation is that you can prove that the Berry phase will still 0 is this phase. But if you very close the boundary, the phase boundary, you will find, however, the effective R will encircle origin, and then the Berry phase will again be pi in the infinite time. So you recreate a Malone fermion in the infinite time. So, and it always depends on this R, effective R. So this effective R depends on initial R dot final R, and this is a final vector. So if you want to understand the phenomena, you have to understand how this Berry phase will be 0 and inside the same phase. Because if you go over the phase boundary, it always creates 0. But inside boundary, you can have different situation. And we study the x is mu, the original mu divided by 2, x prime is mu prime divided by 2. Y is defined as a pairing parameter here for the p wave. So you find, if we fix one initial condition, then you find one kind of curve, and under this curve, if you system quench into these points, and then the Berry phase will be 0, and then even inside the same phase, the H mode will disappear. So this is kind of, you quench the system from the initial state.